Hello, everyone. This is Thomas Johnson once again, and this time we will be discussing elliptic curve cryptography. And so, ultimately, we find that elliptic curve cryptography it is at the intersection of quite a few fields of mathematics. It involves the application of number theory. It also involves application of modern algebra. It involves the application of elliptic curves, as the name would suggest. And ultimately, that all comes together into an implementation within the field of cryptography. And it has expanded well into its own subfield in cryptography, and with a high level of significance in its applications in the modern day. And so when we look, so as we examine elliptic curve cryptography, we find that it is in comparison to another standard of elliptic curve cryptography, notably the RSA. And one thing we need to acknowledge for the compare and contrast of RSA and elliptic curve cryptography is that elliptic curve cryptography requires less overhead than RSA to be able to create keys, public and private, that RSA would need more overhead to do. And as a result, it leads to elliptic curve cryptography being more effective and cost efficiency than RSA. But when you start to put in the idea of quantum computing, that's when both will ultimately fail due to the abilities of a quantum computer to be able to factor prime values, which are crucial to the discrete logarithm problem that allows for RSA and elliptic curve cryptography to survive contemporary computers. And so as we take a look at elliptic curve cryptography, we need to look at the Weierstrass equation. And the Weierstrass equation for the elliptic curve is basically a more general form of it, but that can ultimately be condensed down to a form. The Weierstrass equation, it takes up a number of terms, and it's a polynomial. It's a polynomial equation over degree 3, but it can ultimately be condensed down a few terms using fields, using the restrictions imposed by fields implemented on the equation, so that you can get a more simple equation to work with of y squared equals x to the third plus ax plus b. And looking at y squared equals x to the third plus ax plus b, that gives us this condensed formula that we can use for implementing elliptic curves. It should be noted that we can only use a certain subset of elliptic curves, notably non-singular curves. Singular curves are elliptic curves that have a point where if we were to take the derivative with respect to y and the derivative with respect to x, the value of which would be 0. And the problem with that is that singular elliptic curves allow for the elliptic curve, when implemented over a field, to ultimately be isomorphic to other groups, as would be determined in group theory. So basically, other groups could be used because of that isomorphism in order to find solutions within the elliptic curve cryptographic algorithm setup. So we use non-singular curves. main method that is the main method that is utilized to ensure that the elliptic curve that is being used is non-singular is to use this formula: 4a squared, no, 4a cubed plus 27b squared does not equal 0. And that's for if you were dealing with the elliptic curve over, say, R. But if you were dealing with elliptic curves over, say, Z positive, well, Z, all the positive integers, then you will ultimately be dealing with the same formula: 4a cubed plus 27b squared not congruent to 0 mod the order of said field that you were using. So if you were doing it for integers up to, say, 118, then you would be doing it for mod 1 using the formula for mod 118. And as long as that formula is satisfied, you're certain to be dealing with a non-singular elliptic curve, which is what we want. Dealing with elliptic curves over R is problematic for elliptic curve cryptography because R can be calculated back to previous numbers very easily thanks to the computational abilities of computers. So it's best to be using elliptic curves over finite fields, especially with prime numbers, since primes are hard for the contemporary computational devices to factor. And as a result, when we use a field Z sub p, which is where p is some prime number, then we can use that prime number as one, to verify that the group is commutative and cyclic, and two, to ensure that the discrete logarithm problem is ultimately fine-tuned into it, and it allows us to have a group which produces elements that are harder for any computational device to find involved in the calculations for encryption and decryption. And the reason for this is because contemporary computers, not including quantum computers, have an issue with the way the discrete logarithm problem operates, in that it's very hard. It's easy to calculate exponential values, such as 2 squared, 2 to the 8th. It's increasingly hard for a computational device to calculate logarithmic values, especially within the constraints of mod operations that will be generated within the selective finite field of Z sub p, due to the way that the computer is structured to perform its calculations. This does not go well for quantum computers, which will include a different tool set for computations that will allow them to get past the encumbrances of contemporary computers and being able to deal with prime factorization. So for RSA and elliptic curve cryptography, when quantum computing becomes more viable and ultimately can be scaled up to a reasonable extent, then it will be a major concern for not only elliptic curve cryptography but RSA. But elliptic curve cryptography will be especially vulnerable because the fact that it requires limited overhead for creating its keys means that there will be less resources needed for a quantum computer to be able to crack those keys. But that is for when quantum computing becomes scaled enough to be able to accurately target elliptic curve cryptography. And so, looking at elliptic curve cryptography, it has a number of it has a number of operations that it must deal with, and these operations are effectively to handle each case that may come up when you're doing elliptic curve operations. And so there so typically it's regarded as adding 2 points. When you're dealing over real numbers, you can do it geometrically, but when we're dealing over geometrically or algebraically, but when dealing with dealing with the elliptic curve over finite fields, you have to deal with it algebraically. And so there are a number of formulas that are set up to deal with the addition of two unique points, doubling a point on an elliptic curve, and also when dealing with the point of infinity, which is the identity of the elliptic curve group over the finite field. There is also dealing with the inverse of a point, which will ultimately give you the point at infinity, the identity of the elliptic curve group. Yeah, and also, and just genuinely, these various cases are to allow you to easily formulate either code or mathematical calculations to get the result. And when sending a message using elliptic curve cryptography, you will specify an element belonging to the elliptic curve group over the finite field Z sub p, and that plain text message will be a coordinate or element of said elliptic curve group that will then be encrypted. And so the public key will be comprised of a value coordinate called alpha, which is a coordinate that someone selects, beta, zeta, which is a integer between the order 1 and the order of the elliptic curve group over the Z sub p, and then beta, which is zeta, the number of times indicated by zeta that alpha is added to itself. So that coordinate is added to itself, and that is released as the zeta is kept as the private key, and then alpha and beta in the elliptic curve are released as the public key. So zeta is kept as the private key, and other participants in the transaction will also repeat the same process, and ultimately that would generate private and public keys, with the private key being that one value zeta, which will be identified by other variables when drafting problems, by other variables or symbols when drafting problems, and then alpha, beta, and the elliptic curve group would be released to the public so that people could encrypt. And elliptic curve cryptography is especially successful when we have to deal with security on resources that have very limited computational ability, like security cards and those type of devices. And so